And welcome back. And we're moving into our final segment for today. And of course, this is keeping in theme with our first segment. We are actually going to be doing some science experiments on set, which means we got to be very careful, first of all. We have some university students, University of Belize students with us, and I'm going to give them the opportunity to introduce themselves. I have two with me, and John, you have two over there. So.
Hi, I'm Roberto Ramirez, and I'm a double major in biology and chemistry.
My name is Aleesi Chun, and I'm a double major in biology and chemistry as well.
Wow.
My name is Emile Hong. I am a biology math physics major at University of Belize. I graduated from Guadalupe High School, and I'm also the senator at the state for the Bachelor student government for UB.
All right. Good morning. My name is Reagen. I'm a double major at the University of Belize in math and physics, and I graduated from Western College, one of the best high schools in Belize.
Put in the plug.
Aren't you supposed to talk about the best university that you're at? Now, we're grateful, first of all, that you guys came in. And I just want to ask you very quickly, you know, some people shy or run away from science as fast as they can because they think that it can be a lot of hard work. What has drawn you into these particular majors, and what are your aspirations for the future?
My future aspiration is to be a chemistry teacher at secondary school to promote science. And yes, chemistry is hard. It has its subjects, it has its days. But I mean, it's something that inspires you. And if you have a passion for it, then just go for it and pursue your dream, I guess.
Well, for me, it's more of a passion. I don't know what I'm going to do with it as yet, but I know that I want something that I love doing so that it doesn't feel like a job every day. It's just something like a hobby. And why I like science so much is because a lot of the things that go on in the world is that it's so, you can't see it with the naked eye. It happens so fast and so quickly, and it's so small.
Yeah.
And it's just so interesting to learn about it in depth and do actual practicality with it.
Okay, so you love the experiments.
Yes, ma'am.
All right.
And over there?
And over here?
So, I'm interested in studying to be an immunologist. So that's why I'm picking biology, math, physics. I want to get a lot of exposure, like to be really marketable. Because with math, you could do things with statistics. You can learn how to analyze. With physics and biology, now I could explain things in two perspectives. So that's why I want to go into the medical field with this background to understand.
Deep. That's very deep. And
My future implication is become a meteorology using math and physics.
okay.
I'm trying to reach in there. I know it's been a rough road for me. With the physics, late night studying, hard work. Mr. Lewis, he guided us through, and I'm here today doing experiments on.
Do you have a favorite meteorologist from Belize?
Frank Tench.
All right, I love that.
Excellent.
Yeah.
All right. So
So we're gonna jump into some experiments, right? And who wants to start first?
all right.
You guys have been
we
preparing.
could get started first.
Yeah?
Want over there or here? Over there.
There.
All right. So here we go.
Oh, you're throwing it over to us. We'll take it. We're ready,
take it.
right?
All right, then.
Okay. So tell us what you have, and I'll move this. This is not a part of your experiment. Tell us what you guys are demonstrating here. Go ahead.
In this experiment, I am presenting osmosis. Well, I'm going to present on reverse osmosis, but first we have to understand what is osmosis, then we can define what is reverse osmosis. So reverse osmosis is a technique that we can use to purify water. There are many ways we can achieve that, but I'm going to focus on reverse osmosis. So first of all, what is osmosis? Osmosis is a process where we have movement of water molecules from through a semi-permeable membrane from an area of high concentration to low concentration. What does that mean? Well, it's basically that water wants to stabilize itself. So you have an abundance of water here, a good amount of it, and then you want to transfer that to where there isn't much of it. So the movement of these particles or these molecules will go through a semi-permeable membrane. This semi-permeable membrane only allows water molecules, small molecules to go through, and it acts like a barrier for large molecules like salt or sugar,
Like a
algae.
sieve.
Yeah.
Yeah. So what are we seeing here?
Here we have two concentration of sucrose solution. Here we have
Sugar solution,
Yeah.
right? Okay.
Yeah, sugar. This we have a 10% and here we have a 20%. So basically what we are doing is that the sucrose, we are improvising and we colored it green.
The green bulb here.
Yeah, we're the green bulb. We put that to demonstrate like water that contains dirt. It's filthy. It's and we want to see which one will absorb the water faster.
So we see a difference here. We see this one has become a little bit more green, and this one, I guess is it colored at all? No,
Yes.
just slightly. So this is
Slightly.
10% and 20%. What is the difference between these two reactions?
The 20% is more concentrated. So this has a more osmotic pressure, and it pulls the water molecules and from the high concentration area, which is this, to the low concentration, which is the water. So this one, you have, as you can see, the water level is higher than the 10%.
Yeah.
Because this pulls more of the greater osmotic pressure that it has than this one.
Okay. So how would this be used in real life?
Well,
You want to use that?
the this is osmosis. Osmosis, right? As we have an understanding of it, it's just moving the water particles from
This is what you have set up here, yeah.
This is that one.
Yeah.
this right here. So reverse osmosis is
The opposite.
the opposite, is exact opposite of it. So here we will have the water, the filthy water coming in, and the difference between reverse osmosis and osmosis is that this happens naturally. It doesn't need any kind of it doesn't need any energy to be added to it. This happens on its own. But in reverse osmosis, pressure must be added in this system. So as the filtered water is coming in, pressure will come in to oppose the osmotic pressure that will allow the water molecules to push out and the impurities to stay in. And once having that, the energy that is pushing the water molecule, the water out, it will be collected and then transferred to a tank, and the impurities will then leave out and will be discharged. And so this is just basically one way of the purification of water. Some water companies use this system set up right here.
Okay. So in other words, what happens here is a natural process. As you see, it's just sitting here with nothing taking place. If you had additional pressure applied to it, that's where you would move into reverse osmosis,
Yes.
right?
Yes.
Fantastic. All right, good. So we got our first experiment down. Thank you so much. You're getting some practice with those teaching skills?
Teacher showing.
So what we have here is electrolysis. So we did a little makeshift electrolysis chamber and whatnot. Sadly, my copper wire is like releasing its copper.
Oh, no.
So I'm getting a copper precipitate. But right now I'm just focusing on the hydrogen. And as you can see, there's a significant amount of hydrogen gas in here. So what happens with electrolysis is that when you connect these two wires to the battery, it creates a flow. It's like a flow of electrons.
Okay.
So ions that are very rich in electrons that are negative will come through here. And the electrons that it releases it goes through the wire, comes through the battery, and comes here, so that it can give ions that are very electron poor. It's
Okay.
ions, so it can be liberated and turned into oxygen gas. Because hydrogen is basically two hydrogen. Water is basically two hydrogens and an oxygen.
H2O.
H2O. So as if I had gotten oxygen gas, they'd see that there'd be a 2-to-1 ratio, whereas I'd get a lot more hydrogen gas than oxygen gas.
Okay. So the electricity flowing through the copper, right? Going, and this is water.
Yeah.
All right. So this is what you're talking about, and we have built up the gas here just through that process.
Yeah.
Now explain this to me in real life terms. How is
in
it
real
used?
life terms? Well, in a lot of different countries around the world, they collect hydrogen and they store energy in hydrogen gas. And this when they do this process, it's a lot eco-friendly because your carbon footprint drops way low, so you're not emitting any any carbon towards the atmosphere, which is like damaging the ozone layer and whatnot. So it's very eco-friendly, and it's a lot. Although it's a bit expensive to do, it changes the whole perspective on how you do and how you get energy and how you use energy. Because now in today's in this year and this era, there are a lot of cars that has they store energy as hydrogen.
Okay.
And the very key thing about hydrogen is that it's flammable.
Very flammable.
And what happened in the past before, it's lighter than helium. So if we'd gotten a balloon and we'd open it and collect it and we tie it, it'd probably float up. But the only problem is that if it has any like ignition or any fire close to it, it's gonna pop. So this relates to a disaster that happened way back, and it's a very tragic disaster where that they had a Zeppelin balloon, and the Zeppelin balloon was filled with hydrogen gas. And while they were trying to land, something happened between the chambers between the whole balloon that had hydrogen and the whole balloon containing passengers and everything exploded. So it was a very sad day.
Yeah.
So now that a lot of companies today use helium because it's a noble gas, it's an inert gas, it doesn't react, and it's light. So you use it, so it's
So it has the same effect, but not as dangerous.
Yeah.
Okay, great. So thank you too, and now we're moving over to John.
That's right. It's
John,
actually.
you have a contraption in front of you.
Yeah, I
don't know what
noticed.
that is.
You noticed, right?
Yeah.
We've got lots in front of us. We've got Emile along with Reagen. These guys are, they're professionals. It seems that way from just the way they hold the microphone. We know for a fact they're professionals. Polarity of water experiment and its significance. Now, Emile, Reagen, tell us what's going on here. What's the contraction that we've got here? What is this?
This is a Van der Graaff machine. This is a statical generator used to generate charge. When this generator is plugged in, this had a motor inside that spin this rubber around. Based on the triboelectric series, this rubber is negatively charged because the triboelectric series materials lower down are negatively charged and materials higher up are positively charged. For example, Emily here is positive charged because her hair
is down. So you're telling me, so you're telling me if this is plugged in,
it's generate a motor, and the motor causes the rubber inside to rotate, and the rubber is a negatively charged. It gives off negatively charged electrons to this dome, and the dome is a distributor of charge.
Excellent. So is there any part of this country that we use materials like this?
Not basically, we use it in our physics study.
Okay.
But it has its advantage because if, for example, if we have a lightning storm, buildings higher up can be affected, but because the charge is attracted to pointed objects, that's why buildings are sometimes made it a pointed object to perceive the charge, so to discharge it to the ground.
All right.
Yes, so we mostly use the Van der Graaff to study charge in a safe environment. So before we get into describing the polarity of water, you need to understand that there are two flavors of charges, positive and negative.
Oh, they're flavors?
Yes, they are flavors. And there are two laws, which is that like charges will repel and unlike charges will attract. So you need to keep that in mind.
So positive loves negative, but they don't like another positive. Right?
So with the Van der Graaff, we're going to show you that it could generate charge.
Okay. So we're heading up. Let me hold your microphone.
So we're talking about static.
Yes, static
Static.
electricity.
All right. So here we go. All right. So we're turning on. The rubber is moving.
The rubber is rotating, so now the rubber is giving off negatively charged electron to this door. So we will demonstrate that using our helium light bulb,
So that's a light bulb that you've got in your hand.
which is made from helium gas.
Okay.
All right, make sure the camera can see it. Like bring it over a little bit more. Yeah, thank you.
All right.
Ah.
As you can see here, the dome is at a higher potential level than the helium gas, and I'm a conductor of electricity because I'm made of molecules of water, and water is a conductor of electricity.
One of the greatest conductors of electricity.
So when I place this charge this is from a higher to a lower. From a higher to a lower means that electricity will flow.
Bring it out just a little bit
Okay,
more
a
so
little
we
bit
can
more,
see.
yes.
We're getting to see the fun, but we want the people at home to see it as well.
Excellent.
So you can see here that the circuit is complete.
And this is a great explanation of those balls that you buy that you can touch as well.
You touch
know
the
the
ball,
ones that
yeah.
you touch and it moves around with your hand. What are they called?
I think they're called a plasma.
Plasma balls, right?
For some reason or the other, a
Yes.
while ago, putting my hand next to it, I could feel the hair on my arm are actually raising. What's the reason for this?
Because your body is, you are a conductor of electricity. Because
Mike,
you're made of positive and negative electrons.
Okay.
So what happens is that you are getting charged. So what happens is that your hairs stand out because they are the same charge and like charges repel.
Yeah.
To demonstrate to
All right,
you.
sure.
I love when you show this demonstration. Let's see it.
Yes. So
You're standing here?
yes.
All right, let me hold the microphone.
Why I have to stand here is because I have to be insulated in order to make sure that I could get charged. If I just stand here and then just touch it, nothing will really happen because I'm grounded. So
Okay.
charge always travels through the largest conductor, and Earth is really large and holds all the charge. So it usually goes down the straightest, the easiest path, so it always goes to the ground.
Okay.
So if I insulate myself, I will charge myself and then be able to show you that that this indeed charges up, and I could also be charged.
Okay. So demonstration.
Let's see.
We're waiting for it.
And we're looking at the top of her head. That's what we're looking at.
So what's happening is that
Give us some time to get that on.
the ends of my hairs are getting the same
Yes.
charge, and so they're repelling each other, and so the strands just go out of way. They separate. All right. The lamp.
You kind of look like how I do sometimes to the news. Is there a way to reverse it?
So in addition, I could also transfer my charge because
There you go.
That's a shot.
you know why that happened? Because you're grounded, so and I'm charged. If I touch you, all the electrons will go straight
All
down.
right, please don't touch. Please don't touch.
It's at a high potential.
Okay.
Yes, so all of the higher charge goes down to you.
So with a charge like that, because I got shocked a while ago, with a charge like that, and I could feel the beat. Can you tell me what in terms of electricity? Was it like a 110 or 220 in terms of electricity? What was that like for me?
Well,
I felt a shock. That was a shock directly in my hand, and it felt like a beat. So can you tell me, converted to electricity, what was it like, a 110 or a 220 in terms of electricity flow?
well, what this generates is a lot of volts, yes, but the current is really, really small. So you don't, it won't like, it's not very dangerous for
okay.
you. So I guess I'll say it's like really, really small amount
Okay.
of current.
In other words, John, it didn't hurt you that
Yes.
much. Stop trying to say this hurts you. Yeah.
So if I touch that lamp, the charge will go through, and the same way it's going to light. So you can already see that it's
There you go.
because all of it is going through here and going down to the ground. So that's how this can charge, and we could study charges with the Van de Graaff.
All right.
And that was just
It still has you. Take it off.
Yeah, you could turn it off.
Actually, I'm still charged. charged.
Okay, so
Yeah.
I'll put the microphone here, and then you can pick up the microphone. Okay. So why did you touch his hand?
Because actually I touched you first.
Yeah, you touched me
To
first.
ground, to discharge myself,
Okay.
to get rid of all the charge.
All right. So we could pick up the microphone now without being shocked. Okay,
of
there you go.
course.
There you go. Thank
All
you.
right. So following, we're going to talk about water.
Okay.
Now, water is polar. Polar means that it has a slightly positive side and a slightly negative side. And at the same time, it's neutral. And so it's a neutral molecule, but it has slight positive, slight negative, and that's because oxygen is more electronegative than hydrogens.
Okay.
So when you imagine the structure of an oxygen molecule, you could imagine the Mickey Mouse head. And then the ears are the hydrogen atoms that orientate to the top, so that part is positive. And then you could imagine the head, which is the oxygen, and to the bottom, that's negatively charged. So this polarity of water gives it the ability to interact with charges as well,
Okay.
with different attraction, with the same laws that like charges repel or unlike charges attract. So what we're going to show next is that if we pour water, what do you expect to happen?
Well, it will just stay right there in the container.
Yes, it just
It falls
falls
in the
down.
container,
It just
yeah.
falls down. And then the only force that's acting is gravity.
Yeah.
Okay.
But if we introduce charges and electricity, that's two forces that are going to happen. So it's going to fall and something else would happen.
All right. Let's see
Well,
what
we're out of
happens.
water now. Okay, John, you can help out.
You sure? All right.
Just
So what do you
don't
want me to
touch
do? All right.
Yeah.
Yeah. So what I'm going to do is to charge myself.
The container.
Okay.
Yeah.
Charge myself. Well, as you can see, it's already getting attracted to
It's actually sprinkling.
You can't move it, yeah.
Can you move it over there? Move this. Okay, so water is neutral, but because it's polar, it has a positive side and a negative side, and so it could orient itself because I'm charged. So
The water's trying to come towards you.
yes. It doesn't matter which charge I am right now, it'll still attract because it has a positive side and a negative side.
Once there's any charge,
Yes.
positive or negative, it's going to move towards
Yes,
it
it's
because
going
of its neutrality. Go ahead, let's see it again.
Pour a lot.
Oh wow.
Look at that. So gravity loses in this sense.
No, gravity still acts, it's falling down, but
Okay.
I introduced the second force, which is the electric force,
It's
to
actually
attract,
pulling it away. Yes.
unlike charges attracting. So that's how that's the evidence that water is polar. You need to acknowledge that it has slight negative and slight positive charge.
Okay.
All right.
So
There
I'm
you
still
go.
charged. I still have my hair. So to discharge, you'll notice that the hair will fall down.
Just like
Yes.
that.
Excellent. Excellent.
All right, guys, we're quickly running out of time. So I know we have one more demonstration to do here. And who's going to take this
I'm
one?
gonna explain this
All
one.
right, go ahead.
Right here is a multimeter,
Okay.
and this is used to check a lot of physical properties of water that it has within it. And this is a probe. So you dip this in the bucket of water that I have down here.
Okay.
And to get a full reading, you'd probably have to wait about a minute or 3.
Okay.
So because of the time, I'll just say what all is here.
Okay.
So we have temperature of the water, so what temperature it is. So it says right now it's getting its reading. So it's around 20, 22 degrees Celsius.
Okay.
It has salinity of the water. Like how many, like if it's salty enough, how much
so the
salt,
salt
in
content.
it, the
Yeah.
salt content in it. And then oxygen dissolved percentage, meaning the percentage of oxygen in the water itself.
Cool. Right
So,
there.
and the other one here, it's just in a smaller unit of oxygen in the water. And we have right here the pH of the water, if it's acidic or if it's basic or if it's neutral. So right here is the
Okay.
pH. Finally, we have conductivity of the water. And conductivity, you'd think that if it can conduct electricity or whatnot,
Okay.
but actually is that if it has like the covalent bonds within the water itself in that, because it's kind of dirty. So you'd see what all it's bonded to or whatnot in it, what's all its content in the water itself. And right here we have a colorimeter. Right, this here is that you'd get the chemical properties of the water. So see if it has chlorine, a chemical, I forgot the name of it, but I think it's just the...
You can help us out. What is it?
What?
It's the colorimeter that measures the chemical parameters.
Parameters.
Okay.
That's where parameters. So it just basically reads if it has phosphorus in it, if it has like chlorine in it and whatnot. So,
Yeah.
And this over here, this large contraption right here. It's basically a probe just like this one, that one over there, but it's just a lot larger and it's a lot more sensitive than the other one, and it's used for marine purposes.
Okay.
So
And of course, this is a very important tool in your water quality studies that you conduct. You know, I gotta say, you guys are completely impressive in the level of interest that we've seen in the projects that you brought here today, and we really appreciate it. Unfortunately, we're out of time, so we can't play Mad Scientist anymore, but you guys get to go back to school and do it. It just means we're done. All right, so we gotta go ahead and take our final break. Thank you to the University of Belize for partnering with us on this science experiment segment, and we're gonna take a break and be back in a few.